Hello and welcome back. In the last video we discussed the definition of Laplace transform, Laplace inverse transform and the motivation, and we discussed about some basic Laplace transform. In this video we are going to prove some of these bits and rest of these you please prove them as an exercise. Okay, let's start with the constant function. So first we want to find out Laplace transform of a constant function. If you remember, the definition of Laplace transform of ft is integration from 0 to infinity e power negative st ft dt. ft dt. So let's find out the Laplace transform of constant function. So it should be integration from 0 to infinity e power negative st. Our function is c. Now c is constant, so you can pull it out. Integration from 0 to infinity e power negative st dt. And integration of e power something is e power negative st divided by negative s, and the limits are from 0 to infinity. We first substitute the upper limit. So if you remember, the graph of e power t looks like this, right? This function is going towards negative infinity, so it's basically decreasing and decreasing, so you will get a 0. It's minus, so upper limit minus, you substitute the lower limit which is 0, so you will get t is 0, so e power 0 is 1 divided by negative s. Negative will cancel out and your answer is c over s. So we verified the first one over here. As we discussed in our first video, we are using the abbreviation a to infinity for limit b going to infinity gt a to b. We are using this abbreviation. One more thing to observe here is this e power negative st approaches to 0 only if this s is positive. If t is going to infinity, e power negative st approaches to 0 only if this s is positive. So this Laplace transform is defined for s greater than 0, for s positive. In general, the Laplace transform is defined for s greater than some a. Okay. So let's see second one. Let's prove the Laplace transform of t. Let's see what's the Laplace transform of t. The formula is integration from 0 to infinity e power negative st times t dt. Okay, so here we will need the integration by parts. So we need to choose our function u and function v using the rule Liat. t is algebraic function, so we choose it as u. So let's write down this as 0 to infinity t times e power negative st dt. So our t is algebraic function, so this is u, and exponential function whatever left is our dv. So u is t, so du is equal to dt. V is e power dv is e power negative st dt. So v is equal to e power negative st divided by s, right? Integrating both sides. And our integration by parts rule is u dv is equal to uv minus integration v du. So let's see what we will get. So u, which is t, times v e power negative st over s minus v e power negative s, this is divided by negative s. Negative st divided by negative s dt, right? And the limits are 0 to infinity. So for the first term we have t over s e power negative st, negative negative will be positive, and integration of e power negative st, we will divide by negative s again, so it will be s square with a negative sign, so it will be negative again, and the limits are from 0 to infinity. When we will substitute the upper limit, e power negative st approaches to 0, so we get 0 for both the terms. When we substitute t equal to 0, the first term will be 0, the second term is going to be negative of e power 0, so 1 divided by s square. Negative negative cancel out, so our answer is 1 over s square. See how easily this follows, right? You just need to use integration by parts. Similarly, you can verify t square, t power n, and next, so we verified for the constant for power t. For t square, t power n, you can verify by yourself. Let's see e power at. So next we are going to discuss the Laplace of e power at. By definition, it's integration from 0 to infinity e power negative st e power at dt. If base is same, we add the exponents. So 0 to infinity e power a minus s times t dt, and this integration we know is e power a minus s times t divided by a minus s, and the limits are from 0 to infinity. So first we substitute the upper limit. So if we substitute the upper limit, it will go to 0 if a minus s is negative, right? It means s is greater equal to a. In that case, when we substitute our upper limit, we will get 0. And then if we substitute 0, our numerator will be 1 because it's e power 0. E power 0 is 1. divided by a minus s, which we can write as s minus a because we had a negative sign over here. So Laplace transform of e power at is 1 over s minus a for all s greater equal to a. For other values, the integral diverges. Let's discuss next about this Heaviside function. What is the Laplace transform of Heaviside function? T minus a. So remember, the definition of Heaviside function is ut is 0 if t is less than a and 1 is for 0 if t is negative and 1 if t is greater equal to 0. Now we are going to use t minus a, right? So this function is 0 if t minus a is negative. T minus a is negative. It means if t is less than a, then this function is 0. If t is greater equal to a, this function is 1. So the Laplace transform by definition is equal to 0 to infinity e power negative st ut minus a dt. If t is less than a, then this Heaviside function will be 0. So this integral is reduced to integral from a to infinity e minus st dt, which is integral of e minus st divided by negative s. Lower limit is a, upper limit is infinity. If you will substitute in infinity the upper limit, you will get 0. If you substitute the lower limit, you will get e minus at divided by negative s, which is same as e power negative at divided by s. Right? Similarly, you can verify other properties in the table. I'll encourage you to prove all of these property, and in the next lecture we are going to discuss about properties of Laplace transform. Bye bye. Take care.